Hi, I'm Bethan Massey, and welcome to this McDermott Alpha Electronics Solutions mini-webinar, where I'm going to introduce some of our brand Electrolube solutions for automotive parts and discuss factors to consider when looking at thermal management of electronics. As you can see, Electrolube have a wide range of products suitable for the automotive sector, from thermal gap fillers for heat dissipation in electric vehicle batteries and thermally conductive resins for e-motor potting, to conformal coatings for control module PCBs, and resins with good signal transmission for sensor encapsulation. Here we can see details of some of the types of materials offered under the Electrolube brand. Some of the principal functions of these materials are to help reduce hotspots by conducting heat away and to ruggedize assemblies so that they can function in harsh environments. On the heat reduction side, we offer thermal management materials in the form of pastes and gap fillers to help facilitate thermal transfer. And on the ruggedization side, we offer conformal coatings to protect PCBs. In the middle, we have our potting resins, which offer both environmental protection to the whole assembly and thermal conductivity to allow heat dissipation. I now want to focus more on the thermal transfer side of that diagram, highlighting why pastes, gap fillers and resins are so necessary. Firstly, why is thermal management important? Well, this is simple. It's well known that allowing parts of an electronic assembly to overheat will at the very least reduce its performance, if not cause outright failures and even fires. If this heat production can be directed away or spread out, the assembly will work more efficiently and reliably, improving operational lifetime. So, how is heat directed away? Typically, the main tools are coolant systems or highly thermally conductive metal heat sinks and casings, which are in contact with the areas and components expected to get hot. These help to radiate the heat away from these specific areas and prevent hotspots developing. However, their effectiveness can be greatly improved by the use of thermal management materials. If we could zoom in to the heatsink device interface, we would see that the two surfaces are not perfectly mated and there are small air gaps. And air is a terrible conductor of heat. However, if a thin layer of thermal paste is applied, this eliminates these gaps and dramatically improves thermal transfer. Our materials are available from around 0.9 to 6 watts per meter Kelvin, but actually, a higher thermal conductivity value does not necessarily always mean better performance, as I will now discuss. There are several different methods of measuring thermal conductivity, and values obtained using different methods are not directly comparable, which is why we always recommend to test side by side in application where possible. Thickness of material also has an effect, as applying more than necessary increases the distance the heat has to travel to reach the heatsink, increasing thermal resistance. Fixed dimension materials such as gap pads also can have increased thermal resistance, both due to their thickness and because they do not conform completely to the surface, leaving some air gaps remaining. This can be seen in real-world data. Temperatures were measured for a device and a heatsink assembly alone, and then with different thermal management materials applied at the interface. We can see that the best performing material, number 3, does not have the highest stated thermal conductivity, but delivered the greatest reduction in device temperature. This was due to also having low thermal resistance due to the factors we discussed here. This concludes this mini webinar. Thank you for your time. If you would like more information, please do not hesitate to contact us. Thank you.